Hello friends, I welcome you in lecture number 1 on heat equation. In this lecture we are going to understand the mathematical model governed by heat equation, and we will see that how we can find out the solution of that mathematical model with some initial and boundary conditions. So heat equation is also known as diffusion equation. Some authors are using this word diffusion equation for heat equation. So remember these both words, either heat equation or diffusion equation. Now heat equation is important partial differential equation, and we are going to understand the mathematical model for this equation. So suppose we are interested in the temperature distribution in a thin metal bar. Suppose this is a metal bar or metal rod of homogeneous material, and suppose we are interested in the distribution of temperature in this metal rod or metal bar, and here it is assumed that there is no flow of heat through this surface, that this metal bar is made up of that type of material which is impervious to the heat outside that part. And here also we can say that there is no heat flow on both sides of the metal bar. So in that case we can use this word also, that metal bar or metal rod is laterally insulated. Laterally insulated means there is no heat flow from these sides of the metal bar. So with this assumption, and suppose this end is denoted by capital A, this end is denoted by capital B, and the length of the bar is say capital L. So we are considering a thin metal bar or metal rod of length L with ends denoted by capital A and capital B, and we assume that bar is laterally insulated. That means no heat can flow through the sides of the bar. This is upper side and this is lower side of the metal rod, and there is no heat flow through these two sides. In other words, we can say that the metal bar or metal rod is laterally insulated. And suppose this bar is heated with some initial temperature. Suppose at time t equal to 0, temperature is some function of x, say fx, and this is for all values of x in this bar, that is x lies in between 0 and L, and we are interested in the temperature distribution at any position x and at any time t. Suppose this bar is heated, and suppose after some time t and after some position x we are interested in the distribution of temperature. Then to find out that distribution of temperature, we have to solve the equation which is known as heat equation, which is given by del u by del t equal to c square times del square u by del x square. So this solution of this heat equation is nothing but temperature distribution in a metal bar of length L at any position x and at any time t. So our main objective in this topic of heat equation in this course is, suppose we are given that we have this type of metal, homogeneous metal bar, and suppose this is the initial temperature, that is temperature at t equal to 0, and how to obtain the temperature distribution at any position x and at any time t. And here we are going to consider two types of boundary conditions. We will consider first case of boundary conditions as that the temperature at both the ends is 0, that is u equal to 0 at x equal to 0 and u equal to 0 at x equal to L, that is temperature at both the ends of the bar is 0 for all values of time t. This is first case. We are going to discuss the solution in two different cases, and these two different cases differ for boundary conditions. The only change between these two cases is boundary conditions. In first case, we assume that both the ends of the bar are having temperature 0, and in second case we assume that both the ends of the bar or rod are insulated, that is temperature gradient is del u by del x at x equal to 0, that is temperature gradient at x equal to 0 is 0, and temperature gradient at x equal to L is also 0. This is for all t greater than or equal to 0. This means we can say that both the ends are insulated. Both the ends of the bar or of the rod are insulated. This means no heat can flow through the ends. There is no passage of heat through the ends. Suppose I have two ends A and B, then ends are insulated, that means no heat can flow through the ends, and physical experiments shows that the rate of heat flow, that is del u by del t, is proportional to the gradient of temperature at that point. So del u by del t is proportional to del u by del x, that is given by physical experiments, that is the rate of heat flow is proportional to the temperature gradient, that is del u by del x. Now if we assume that both the ends of the rod are insulated, that means no heat can flow through the ends, that means del u by del t is 0, and because del u by del t is proportional to del u by del x, del u by del x is also 0 at those ends if they are insulated. So this is another case of boundary conditions. So we are going to discuss the solution of this heat equation with initial temperature given by some function of x, say fx, and these two types of boundary conditions. First we will solve the heat equation in the case that the ends are set at temperature 0, that is the temperature at both the ends is 0, and another case we will consider that both the ends are insulated, that means no heat can flow through the ends, and in that case temperature gradient at both the ends will be equal to 0. So we are going to discuss the solution for both the cases one by one, and we will derive the standard formula of the temperature distribution in both the cases using the method of separation of variables, and we will discuss the problems based on both the cases in this lecture series of heat equation. So what you have to remember is that we are interested in the temperature distribution in a thin metal rod or metal bar of say length L, and we are interested in the value of temperature at any position x and at any time t, and this model is governed by heat equation given by del u by del t equal to c square times del square u by del x square, and we consider initial temperature as some function of x. So here we have only first derivative with respect to time t, therefore only one initial condition is required, and we will require boundary conditions. So we have two types of boundary conditions. First type is both the ends are having temperature 0, that is the first case. This is for all t greater than or equal to 0, and this is for all values of x in between 0 and L. This is first case. Another case is same equation, del u by del t equal to c square times del square u by del x square. Same initial condition, that initial temperature is given by some function x, but in this case we have the assumption that no heat can flow through the ends. So how to decide temperature distribution at any point x and at any time t? So in this case these boundary conditions are different. Here we have, instead of u, value of del u by del x at x equal to 0 is 0, and value of del u by del x, that is temperature gradient, at x equal to L is 0. So you have to be careful. You will be given the problem of heat equation and you have to decide that which case is given. Either the ends are having zero temperature, or temperature gradient is 0 at the ends. So in this case they will mention that both the ends of the metal rod are insulated. That will be specified in the given problem, that ends are insulated, and here you will be given value of temperature which is 0 at both the ends. So we will discuss the solution of different problems related to both the cases one by one in upcoming lectures. First we will start with case 1. We will find out the solution of this heat equation satisfying these two types of initial and boundary conditions using method of separation of variables. Then we will derive the general formula for this case. After that we will solve the problems of case 1. Then we will go for case 2. Here also we will derive the formula to solve this type of case whenever both the ends are insulated, and then we will do some problems related to this case. So we will go in this way one by one, and I suggest you to watch each and every lecture in a series. Then only you will be able to solve the problems of heat equation. So this is all about this session. I hope you like it. Thanks for